My name is Stephen Goodman, and I am presenting our work titled SPECTRA, Personalizable Sound Recognition for Deaf and Hard of Hearing Users through Interactive Machine Learning. Sound carries rich information that can heighten our awareness and enrich our daily experiences, from traffic passing on a busy street, to the calls of loved ones from another room, to footsteps from behind us. However, this information may not be accessible to people who are deaf and hard of hearing, or DHH. To support sound awareness for DHH users, sound recognition tools have proliferated, both in the research literature and in commercial applications. Android and iOS devices include pre-trained sound recognition models for about 15 generic sound categories, such as appliances and alarms. However, DHH users of these tools weren't satisfied with their accuracy and desired a wider range of available sound categories. Part of the problem is that sound interests among DHH individuals are diverse and influenced by cultural, contextual, and personal factors. For example, a deaf person who signs may be less interested in spoken conversations than a hard of hearing person. Sound preferences can also change with social contexts, such as around family versus strangers, and physical locations, such as at home or while moving. Personal sounds may also be important, like a child's voice or unique noises in the home. Given this diversity of needs, a one-size-fits-all sound awareness solution may not be tenable. Instead, the varied needs of this population may be better met empowering users to personalize a sound recognition model themselves. Some personalization options are already available, such as toggling whether to receive alerts for each sound or extending pre-trained models with a brief recording. While these automated approaches are fast and easy, they lack transparency and control. The model remains a black box, which can limit trust in long-term use. Interactive machine learning, or IML, offers an alternative approach for DHH users to build specialized tools for their needs and developing an understanding of the system's strengths and weaknesses. However, most literature on interactive machine learning assumes that users have domain knowledge and can understand the model's data, which may not be true for DHH users in audio. Prior work has begun to investigate the potential of IML for sound recognition, but in one case did not provide non-auditory feedback, and in a second only focused on the data collection step of the ML pipeline. Our research aimed to investigate how interactive machine learning may influence DHH users' views on sound recognition and identify effective mechanisms for personalizing these tools. To explore this further, we built SPECTRA, an accessible interface for DHH users to collect personal audio data, construct a training dataset, and carry out iterative model testing and refinement. First, users choose the sounds they want to recognize, like a faucet running or a door knock. To support users when recording, SPECTRA includes spectrogram and waveform visualizations. Live visualizations can reveal their soundscape, while static representations show the recording's contents. To contextualize the data during training, users can also add annotations to note important details not captured in the visualization, like a recording's location or variations of the sound. Alternatively, for sounds that are difficult to capture, users can find a recording using videos from the AudioSet library. After recording, the next step is curating a representative training dataset. Each recording is automatically segmented into visualized examples, and users find mislabeled or unsuitable examples to exclude them from training. SPECTRA also includes a three-dimensional clustering visualization to assist users with understanding the similarities and differences among their sounds, and to explore how their dataset may be interpreted by a sound model. Users can compare examples within or across different sound classes and highlight individual points in the selection grid, such as to identify outliers. For this dataset, the clustering suggests that the model should be accurate for the faucet, but struggle to differentiate between the similar background noise and microwave sound, which overlap. When ready, users train a new model and move on to the test page. Here, users can quickly test the model's predictions in practical use. As expected, the microwave and background noise are getting mixed up, but the faucet performs well. If users aren't satisfied, they can return to collect more data or adjust the training set. In our evaluation of SPECTRA, we sought to answer, how do DHH users engage with SPECTRA to train a personalized sound recognition model? And how does interaction with spectra affect DHH users' perspectives on sound models and their confidence with custom training? To answer these questions, we recruited 12 DHH participants for a 2-hour single-session remote user study. We did not screen for prior technological experience because Spectra was designed to assist all DHH users interested in personalizing a sound recognition model. However, 5 participants mentioned hands-on ML experience before the session. The study began with a tutorial to introduce Spectra and technical concepts, such as the meaning of spectrograms and clustering visualizations, along with a brief interview and ratings to capture initial expectations. 60 minutes of system use followed, where participants collected data, curated a training dataset, trained and tested a custom model for 6 sounds. To prompt consideration of their data's real-world distribution, we encourage participants to capture variations of each sound when recording. The session concluded with a semi-structured interview to reflect on the experience and capture post-use perspectives. I'll highlight a few key findings next. Participants used Spectra's interactive clustering visualization for insight into the similarities and differences among their audio data. It was a critical aid to the interactive ML process, offering an accessible way to explore the structure of their training dataset. As P8 put it, quote, an understanding of what's happening under the hood. Looking at the clusters of P10's data here, we can see similarities like the orange stovetop fan and purple background noise. This overlap indicates the model might confuse these two sounds. The faucet is mostly separated from the group, so the model should perform pretty well on that sound. However, these individual green triangles in the center are outliers and possibly should be taken out from the data. Perhaps the most significant benefit of the clustering was in understanding how decisions were shaping the future model. Here's P10's unfiltered data again on the left, along with the final filtered dataset she used to train her model. The clusters are more separated now, which should indicate the sound categories will be easier for the model to learn and distinguish. This iterative feedback loop brought confidence in the quality of the dataset. As P1 put it, quote, it was satisfying to see, okay, like it's actually working what I'm doing. This leads to the second key finding, which is the value of multiple views of information. Participants combined each source of information available to them to build a comprehensive understanding of their data and make decisions about their models. Clustering provided the high-level structure, while waveforms showed individual example contents, spectrograms offered nuanced detail to some but not all participants, and annotations provided further context to aid in decision-making. These were demonstrated in the 2 distinct strategies that participants used to filter their training dataset. Some participants analyzed each example's waveform or spectrogram shape in the selection panel to find unsuitable data, with the clustering as secondary feedback to monitor the dataset's status after making changes. P4, who used this example-centric strategy, noted the waveform's glanceability aided immensely in finding, quote, the background noise versus whenever I was talking. Being able to figure out which example was which, I think that was really helpful. The other strategy used the clustering for analysis to flag outliers and problematic examples, with the example waveform or spectrogram used to provide more targeted analysis. P11 explained his choice of the clustering-centric approach. I was driven by what I was seeing in the chart to eliminate some edge cases and anomalies. Everything is shown together. In the selection panel, I have to compare one by one. P11's comments about efficiency were not uncommon, and the third key finding relates to these perspectives shifting through use of spectra. While we did not find a significant result when comparing participants' pre- and post-use ratings, their statements throughout the session indicated positive shifts in confidence and understanding. No participant returned to train a new model after testing, either due to time or fatigue. When reflecting on the experience, many felt that Spectra required too many interactions to produce a useful result. For example, P3 said, quote, the unchecking was not my favorite. It just ate up time. Participants also shared their ideas for improving the process. Some felt creating completely new models were unnecessary and sought to use a similar workflow to extend a pre-trained model with new sounds. Others sought further automation, like automatic background noise removal or in-situ help, such as P7 suggestions for text reminders pointing out problematic examples. Ultimately, how to optimize the training process while continuing to support meaningful engagement with the model remains an open question. Thank you very much for listening, and please refer to our full paper for more information.